The next type of differential equation we're going to look at is something called an exact equation. Now, an exact equation has to have a very specific form for us even to start. The form that we generally write this as is we say that it's going to be some function of x and y dx plus some other function of x and y dy equals 0. Now, this is the basic form that we should always be able to get an exact equation into. Now, just because it's in this form does not mean that it is an exact equation. The test for exactness, I don't know if exactness is a word actually, but to see if this thing's actually exact, all you have to do is take a look at the function that's in front of the x and take the derivative of that with respect to y, and look at the function in front of the dy and take the derivative of that with respect to x. If these two things are equal to each other, then the equation is an exact equation. Now, the good news for us is solving an exact equation is very, very simple, at least the process is. But let's see why this works. Now, for the few of you that may have already had Calc 3, you're going to see some extremely close correlations between this, the gradient, and conservative vector fields. Now, the idea here is if this is true, we can kind of think about it like this. This looks like a derivative in differential form, right? When we take the derivative in differential form, like if I had y is equal to x squared, then in differential form, the derivative is dy, some function dx. So you can see this looks like the derivative with respect to x in differential form, and this piece over here looks like the derivative with respect to y in differential form. So kind of think about it like this. This then would already be a derivative with respect to x, and then that's the derivative with respect to y. So that means that this would be a derivative of some function with respect to x, then with respect to y. Now over here, this would be the derivative with respect to y, then the derivative with respect to x. Well, if those two things are equal to each other, as we saw when we looked at partial derivatives, if the mixed partials are the same, that means that this f here had to be the same function. So the idea here is, there's some function, if this is exact, that this is the derivative of that function with respect to x, and this is the derivative of that function with respect to y. Or another way of saying this, the derivative of the partial with respect to x of some function of that is what this m of x and y is. And the partial of that function with respect to y of f of x and y is what this n is, this function of x and y here. So think about it. To get back to the function f here from these two things, all I'd have to do is integrate f with respect to y, because we took the derivative with respect to y, that would get us to f. Also, if I integrated m with respect to x, that would also get us back to f. So let's see how this works out. Let's take a look at, our directions here are just going to be solved. Let's take a look at a ugly looking, let's see, e to the x cosine y plus 2x dx minus e to the x sine y plus 6y squared dy equals 0. Okay, let's say that I gave you this messy looking equation here. Now, first off, you should be thinking, just because the form it's in, maybe this is an exact equation. If it's not an exact equation, maybe you could rearrange it to be separable, or maybe you could rearrange it to be first order linear, but since it's already kind of in this form, I'm thinking maybe this is exact. So by looking at it here, our function m would be e to the x cosine y plus 2x, and our equation n, now here's where you're going to make a little bit of a mistake. Remember, in this form, that has to be a plus. So for this to be a plus, we're going to have to distribute the negative, so that would be minus e to the x sine y minus 6y squared. Okay, so if those are our two functions m and n, to check to see if this thing is exact, we need to find m sub y and we need to find n sub x. Well, the derivative of this with respect to y, let's see, there's my only function of y. The derivative of cosine is negative sine. That's a function only of x, so its derivative is 0. Now, when I take the derivative of this with respect to x, that's the only function of x, so the derivative of e to the x is just e to the x. And the derivative of that, of course, is 0. Now, notice that those two things are equal to each other. So this is exact. So, our goal here then, to find the function that we started with, all we're going to have to do is either integrate m with respect to x or n with respect to y. Now, either one will give us our answer, but the problem is there's this integration constant that's going to come into play, and we're going to need both to actually figure this out. So, watch this. My answer is going to be the integral of m, this is m, e to the x cosine y plus 2x dx. That's going to give me my answer. But so is the integral of negative e to the x sine y minus 6y squared dy. Both of those are my answer within an integration constant. So let's start out with this. Let's integrate this one. This one's pretty easy to integrate. Remember, if we're integrating with respect to x, y's are constants, just like derivatives. So this cosine y is just a number. The derivative of e to the x is e to the x. Cosine y. The derivative of 2x dx is x squared plus some constant. However, it's a little bit more complicated than that now. You just can't put a c here. Because remember, we're talking about partial derivatives now. So if we took the derivative with respect to x, anything that only had y's in it was a constant, which means it went away. Kind of like here, when we took the derivative of 2x with respect to y, it completely went away. When we did the derivative of 6y squared with respect to x, it completely went away. So our integration constant here isn't just a numeric integration constant, it's some function of the other variable. All right, let's go ahead and integrate this over here with respect to y. So if we integrate with respect to y, this e to the x here is a constant, so the integral of sine y is negative cosine, so those negatives cancel out, so I get e to the x cosine y minus, when we integrate that, we get 2y cubed plus some integration constant. Now, since we integrated with respect to y, our integration constant is a function of x. Now, here's the good news. We're done with this problem. That's our answer, and that's our answer. That's the thing that we took the derivative of to get these two pieces. But notice each one of them has this arbitrary integration constant in there. So to figure out which or what those arbitrary constants are, set them equal to each other. So let's go over here real quick. So I know that these two things have to be the same answer. So e to the x cosine y plus x squared plus g of y has to be equal to e to the x cosine y minus 2y cubed plus some function of x. All right, right here is a great place to see if you have made a mistake. At this stage, when you're comparing these two answers to each other, any function that has both x's and y's in it, any term up there, better show up on both sides. Here's what I mean. Notice the e to the x cosine y has x's and y's in it, and it's also on the other side. If you have a term that has x's and y's in it that only appears on one side, somewhere back here you have made some type of mistake. You need to go back and see what happens. So those two things will cancel out, and we have x squared plus g of y is equal to negative 2y cubed plus h of x. Right, now this is really easy to solve if you understand what this function notation is telling us. G of y, this is a function that only has y's in it. So if you look at this side and compare it to this side, we have x squared plus some function of y equals some function of y plus h of x, or just some function of x. So by looking at this, you can see that g of y has to be a function of y on this side. The function of y on that side is this thing. So g of y has to be negative 2y cubed. The function of x on this side has to be equal to the function of x on that side. So h of x is equal to x squared. Now remember, I said both of these were our answer. And if you notice, if you go into this one and put g of y in, and you go into this one and you put h of x in, you get the exact same answer. So putting into either one of these, I don't care which one you put it into, we get e to the x cosine y plus x squared minus 2y cubed. Now we have left a little bit off here. Remember, this thing was an equation we had the other side. And what have we left off with our integration? Our integration constant we said was solely a function of x or solely a function of y when we did these pieces right here. However, remember, it could have been a numeric integration constant as well. You kind of think about this, we kind of integrated this side. If we integrated 0, we would get some other integration constant. So once you have your function, it's always equal to another integration constant. That's an actual number integration constant there when you do that. So set them equal to each other, figure out your arbitrary integration constants, which happen to be functions in this case. Then when you get done, replace one or the other. That gives you your function, your original function, and that equals a number. Now, to check this, you wanted to take the derivative of this with respect to x. You should get the thing in front of dx. So in this problem, we should get this piece. Take the derivative of this with respect to y, you should get this piece, dy. And notice if you take the derivative of a constant, doesn't matter what you take the derivative with respect to, you get 0. All right, let's try another example here real quick. Let's go way back over here. Let's see. Let's do dx plus, make me a little bit more room here. Yeah. All right, so let's take a look at another example. This one's going to be actually maybe a little bit easier, but something odd can happen here. Let's call this 3x squared y squared dy. 0. All right, so for this example, just because of the form that it's in, I'm thinking, hey, this might be an exact equation because we have some function dx plus some function dy equals 0. So there's a real good chance that it is an exact equation. So let's give it a shot. So my function in here is 2xy cubed plus secant squared x. My n here would be 3x squared y squared. So think about it like this, think about the mixed partial. Since this was already the derivative with respect to x, I want to take the derivative of this with respect to y. If we take the derivative of this with respect to y, I'm going to get 6xy squared. Since that's solely a function of x, the derivative of that's going to be 0. N sub x, if I take the derivative of this with respect to x, that just gives me 6xy squared. All right, these two are the same, so this is exact. So all we have to do now to find the solution to this is we integrate m, which is 2xy cubed plus secant squared x with respect to x. And that should give us the same answer if we integrate 3x squared y squared dy. Okay, so let's see, if we integrate this with respect to x, y's are constants, so the derivative, the integral of 2x is just x squared, the y cubed is just a constant, and the integral of secant squared is the tangent plus. Since we're integrating with respect to x, any function of y would be our integration constant. Now let's integrate this with respect to x. Again, if we integrate this with respect to x, what are we going to end up with? I'm sorry, integrate with respect to y. What are we going to end up with? Well, the x is a constant, so that's going to give us x squared y cubed plus any function of x. All right, now both of these are our answer. So all we got to do is compare the two, figure out what our integration constants are, and we're done. So let's bring these up here. Let's see, I got x squared y cubed plus the tangent of x plus some function of y has to be equal to x squared y cubed plus some function of x. All right, again, this is a great place to see if you've made a mistake. Any term that has both x's and y's better appear on both sides, and in our case it actually does. So let's see, let's compare it now. Once we cancel those out, plus g of y is equal to some h of x. So all the functions of x on this side has to be equal to the functions of x on this side, so that's pretty straightforward. The only thing with x's in it on this side is the tangent function. The only thing with the x's in it on this side is the function h. So h of x has to be the tangent of x. Now this is a little odd. Here, this is a function of y's, has to be equal to function of y's on that side. Since there's no y's on that side, that means g of y has to be 0. Now notice, if you take this answer here and you put g of y in, or if you take this answer here and put h of x in, you get the exact same answer. So our answer is x squared y cubed plus the tangent of x equals a constant. So that gives us our function. Don't forget, equals a constant, because that's what you get if you integrate 0 on the other side. So exact equations are very, very straightforward. Once you test to see if they're exact, integrate both each one of the pieces, your m and n, with respect to x and y. Those two things need to be equal. Set them equal to each other to figure out your arbitrary integration constants. Once you've done that, you have your solution. Either one of these is your solution. Don't forget to set it equal to a constant. Now, what happens in this case if it is not exact? Well, I'm going to show you a quick little trick in the future to where you can actually take something that's not exact and possibly turn it into an exact equation.